My name is Samy Yousef. I'm PhD in mechanical engineering and now since senior researcher at KTU in Lithuania. So our research group working in recycling and energy recovery from waste in general. Today I'm here to present something from our result related to pyrolysis of metallized food packaging waste. Um, so I will start by short introduction about our research group and what about our research topics. First of all, we started by recycling of electronic waste and then lint generated from washing machine and net fishing and textile waste and banknote, old life banknote and solar cell and epoxy or fiber reinforced epoxy and wind turbine blade and something related to agriculture like mango. So this is like general information about our research group, and we have a lot of publications in this field related to energy and renewable energy and total environmental and cleaner production, more than 10 publication and chemical engineering and recycling and waste management and so on. So today I'm here just talk about recycling of plastic waste. Every year we have more than 300 million ton waste of plastic waste every year. Inside this amount, we have more than 27 million ton metallized or flexible packaging, and we can call it also sheer metallized food packaging waste. So this is the shape of metallized food packaging waste. And this one full structure of metallized food packaging waste. Inside we have more than 4 or 5 layers made from polymer, and in between there is one layer made from aluminium. And total amount of this layer around 5% from total weight. And still until now, a recycling rate of this kind of plastic waste, it is not more than 90% from total weight. So here, the main state of the art of recycling of our research, we started to use a pyrolysis treatment to extract or to convert organic fraction to oil and gas. Then we can extract also aluminium in shape of solid residue mixed with char. So this is our goal. Uh, to achieve this goal, we started by initial experimental work to indicate exactly how many layers we have inside our feedstock. In our case, this packaging food waste by chemical treatment, and this technique we already published in in chemical chemical journal, and by this technique we started to know the amount of or structure of each product from all of them, chips, chocolate, biscuit, Nescafe, and so on. And with, as we can see here, by the end, we have here 90% from total weight, like aluminium, and then 10%, and here, so this is for metallic fraction, and this one related to polymer fraction. Here total weight more than 90% from total weight, here around 88, and so on. So this is the like average weight percent of polymer and aluminium sheet inside our feed stock. And here full structure of these multi layers plastic waste. So at the beginning, we started to study thermal decomposition of this kind of plastic waste based on TGA analysis. So here, as you can see, we have six batches, okay, for different feedstock. This one, number one, two, three, four, five, and number six. This is mixing between all of them, because this is a real situation. In real situation, it is not easy to separate between all of them, because most of separation technologies, they did this one by hand, so will take a lot of time and will be not useful. So based on our layout, we started to study each patch alone, and last one, mixture for all of them. So here, as you can see, TGA and DTG analysis of each batch. Then at the maximum decomposition, here we started to study the chemical composition of generated product using FTRR and GC, and we found a lot of energy product and oil product at this point. So it was like first step. Second step, we repeated again the same work again, but with different concentration of catalyst. And in our case, we used xylot catalyst, ZSM. And we did all work again, and we studied also FTRR and GC again, and we found chemical composition of the generated energy product not the same, started to change a lot. Then for next step, we started to study kinematics of each process using Kissinger, Frau, and Friedman, and so on. So this is the plotting which we made by kinetics. And also we calculated activated carbon at each conversion rate for each batch. And finally, we made simulation for TGA and DTG data using different techniques. So this is for kinematics. And based on optimal conditions, I mean, optimal conditions here, this one, as you can see, we did all TGA experimental work at different heating rates from 5 till 30. So based on FTRR and TGA, 25 degrees, it was like the best condition. So we started to go to up to next level, like a real industrial level, or now pilot scale, to study the yield and chemical composition of the formulated compound. As we can see here, this is our pyrolysis plan, which we designed and built up here in our institute. As you can see here, inside this pyrolysis plant, we have main source of nitrogen, and this is the main reactor. And inside there is capsulate, and inside this capsulate we can put our feedstock, and here heating source, this yellow coils. And by the end of our reaction, we can convert this mixture between all these feedstocks into wicks and char and gas. So here, in our case, we have char, black carbon, and mixed with aluminium, and this is the final shape of residue or char and aluminium. And here also, this is the shape of formulated wicks. Wicks, this is like oil, but with higher viscosity. Then gas. So in our system, we have possibility to check the chemical composition of the formulated gases as a function of pyrolysis temperature. So we did our experimental work till 600 and 700 degrees. So Here in this figure we can check. We started from 0 till 700 degrees, and inside here we have possibility to check concentration of gases inside. Here this is for oxygen and nitrogen and carbon dioxide, hydrogen, CH4 and CO2. As you can see here, for hydrogen, we can get hydrogen at the end or at higher temperature, 700 degrees. For CH4, we can get CH4 around 600 degrees with yield more than 35% from total weight of this one. Also, we can check nitrogen. Nitrogen here at the beginning, it was a 100%, because based on the condition of pyrolysis, if you like to make ideal pyrolysis, so we should to make it in pure nitrogen without any oxygen inside. So till around 500 degree, or 400 degrees, it was only nitrogen. And after this domain, another gases started to generate. So this is like compensate between nitrogen and the other gases. So we can return back again. Okay. So here this is what we got from this unit, composition of gases. And as I said, this is the composition of solid residue, aluminium and char. So here, in order to separate aluminium from this solid waste, we started to make milling, and by leaching, chemical leaching, we can separate black carbon and aluminium chloride like salt here, and by filtration and drying, we can get a pure black carbon and aluminium chloride. So this is for also for analysis of extracted aluminium and aluminium chloride. And here, this is the final yield of what we got. As you can see here, we got wax more than around 20% from total weight, and biogas here, including CH4, H2, and other gases. So more than 62% from total weight, like biogas, and solid waste, solid residue here, around 19% from total weight. And by using leaching, chemical leaching, we can separate black carbon against aluminium chloride. But still here, black carbon needs some functionalization or refining. So here, after extraction, we started to make functionalizations for this black carbon, and finally we got pure carbon black. It is allowed to use it as a filler material or energy product. And here also, so all result here, we got it by online measurement unit, but this is not clear measurement, because by this unit there is some overlapping between gases. So for a device can consider all of them like CH4. So it is not very accurate. But to know exactly the composition of the generated gases, it's better to check by GC, gas chromatography, at different time and temperature. So as we can see here, at higher temperature, we got a little bit of carbon dioxide, and at the middle it was no any almost carbon dioxide, and the majority here at the middle it was C2H6 and so on. For wax, this is what we got from this kind of waste. It is like viscous energy product, and based on FTRR and EDX. It was this is paraffin wax. Also, we did some analysis for generated gas by the end of our reaction by using GC and FTRR. So this is for first step, and for next step, we started to use this functionalized carbon or black carbon as a filler material to prepare nanocomposite nanocomposite panel can use it for structure, light structure in general. So we started to prepare these panels using vacuum using hand up technique to prepare these panels, then cut it to mechanical and impact samples, then check mechanical behaviors of this one. So as you can see here, FBC0, this is our panel without any additives inside, and it was about 180 megapascal. And after mixing with 0.7 from this functionalized carbon, black carbon, we increase it here mechanical strength till almost 220. Also, we did some scanning to know exactly the failure mode of each one. A cross section of this one, as you can see here, we have a big size of epoxy inside, and by increasing loading of functionalized of carbon black inside, this black bulk pieces started to change to small pieces. What mean our failure mode here change it to brittle failure mode. And for impact, this is a schematic drawing of impact test and loading at each point. Here for pure one, as you can see, it is a rhombus without, almost like standard rhombus, and some notches inside. But once the amount of carbon black started to increase inside our matrix, failure started to change to from ductile behavior to brittle behavior. Also, morphology was checked by optical microscope. So this is the summary of our work, and thank you so much for your attention.